Good afternoon, sir.
Yeah, good afternoon. Hello everyone. So do you have any questions from the last class? Okay, so let's start because from yesterday there was a frequent cut of internet. I don't know why. So you may see suddenly I'm disconnected because of the frequent disconnections from Wi-Fi. Let's see. Now it is fine. You can hear me, right? Hello.
Yes, sir.
Okay.
Yes, sir.
Yeah. So any questions? All right. So let me finish first about the isotope effect. So I discussed yesterday that okay, the secondary kinetic isotope effect Kh by Kd. Okay, so if it is normal or inverse, what are the conditions? And it is very easy to remember that okay, loose to tight or too tight to loose. That can also help you to predict that oh, this is the reactions and this is the proposed rate determining step or transition state. That what should you expect, or the opposite way, that you know that a Kh by Kd is you may expect both. It may be like normal kinetic secondary kinetic isotope effect or inverse. Okay, and depending on the outcome of your experiment Kh by Kd value, you can rule out the other pathway, right? Yesterday I told also that how can you distinguish SN1 or SN2 type of reactions, for example number 3, right? Right, all right. So yeah, okay. So next one, I'm going to tell you about. If you have any questions, you can tell me also. So okay. So next, I'm going to tell about some little bit different. That is the steric isotope effect and heavy atom isotope effect. So steric isotope effect. This is an example of biphenyl rings. You can see here there are two methyl groups. This is the methyl groups. X means it can be H or D. So this is the racemization. So you can think about that. This is not in planar. Okay. So this is biphenyl. Okay. So this is just like a binap kind of things. Those are twisted. They are not in planar. So this ring and this ring are not in the same plane. Okay, because of the steric. So it has been observed that if you convert the left hand isomer to the right hand isomers by flipping, okay, you can see that CH3 groups here is a below the plane, and this is just if you twist on the opposite side, these biphenyl compounds are above the plane. Okay, so they are in equilibrium. So the equilibrium constant, okay, it is not like a red, okay, okay, it is equilibrium constant, okay, it's not like a is a fast reactions. So this if you replace this CH3 in X means H or D, then it has been shown that the Kh by Kd is 0.87, means this is a inverse kinetic isotope effect. What about the K equilibrium of this? If you replace H with D, then its rate increase or decrease. If you replace H to D, rate constant will increase or decrease. Increase or decrease? Huh?
Decrease.
It's inverse. So decrease or increase?
No, increase.
Yeah, H to D value is less than 1, right? So D will be the faster than H. Am I correct? Rate
Yes.
constant for K is larger than KH. So if it is a D, then your rate constant is larger than H. This is the inverse. Okay, so what will be the possible explanation? The possible explanation is all about the vibrations. So which will vibrate more, CH or CD? CH or CD? Which vibrates more?
CH.
CH vibrates more. So if it vibrates more, suppose this way, this way, this way, then effectively it's three dimensionally. It's size, you may think about that size, okay, including the van der Waals radii with the vibrations. Its size is larger than CD. Okay, so CD vibration is low, so effectively its size is smaller than CH. Is it clear? Because CH has much more vibrations, it can elongate further, longer. Okay, so effectively the CH3 size is more than CD3. Okay, so you can see here the twisting here, these two methyl groups or two phenyl groups, it all depends on what is the sizes of CH3 or CD3. So since CH3 is effectively larger in size, okay, because of it is more vibrations, okay, larger vibrations than CD. So the equilibrium, the twisting from this side to this side or opposite way is difficult. It needs more energy. It will be slower the rate constant will be lower compared to CD3. Does it make sense? Okay, so you have asterisk here. Whenever you will rotate, then in certain point both CH3 or CD3 will be in the same plane and they will sterically hindered. Okay, so in the same plane, because of the steric hindrance, they are twisted. Okay, so this twisted. So this is decimation, so equilibrium all depends on what is the effective sizes of CX3. Since CH3 is effectively larger than CD3, that's why its rate is lower than CD3. Okay, that's why you see inverse kinetic isotope effect. Okay, and this is originated because of the steric. So that's why it is called steric isotope effect. Make sense?
Yes.
Yes or no?
Yes.
If it is not, I will repeat again. All right, so last one is heavy atom isotope effect. So I told you that what is the magic of CH? So always, whatever the examples of, whenever you will also do a kinetic isotope effect in experiment in laboratory, you will use CH and CD only. Why? Because H is the only one element. If you go to the next isotope effect, its mass get double. It's the only one in the whole periodic table. Okay, so the difference of reduced mass is almost double, right? You can see the values. So the rate constant differences, if it is the primary, secondary, or inverse, whatever it is, you will get the maximum contrast, okay, or maximum changes on isotopic substitutions you will get when you will replace the hydrogen with deuterium or tritium. Not only for that, deuterium is easily available, abundant. It's quite cheap. Tritium, I'm not talking about that. Deuterium. Okay, you can purchase it. It's quite cheap. Okay, it's quite cheap. One of the main sources is D2O, heavy water, that you know from your high school, right? Heavy water. But the same principle, the kinetic isotope effect, okay, you can also apply for other atoms. Okay, but I told you the problems about C13 and C12. Okay, this is the carbon. You can see the reduced mass C12 is 6 and C12 C13 is 6.24. So you can see that carbon 12 to C13, okay, C13, the reduced mass is increasing. How much? 10%, 15%, not double, 100%, right? So the whatever the value of kH by Kd, you will see that will be very small amount. So whenever you will do an experiment of isotope effect using C12 on C13, okay, or suppose N14 and N15, okay, because of the very minor differences of the reduced mass, the value of kH by Kd will be very low. So whenever you will use those isotope effects using those isotopes other than hydrogen, then experiment need to be very carefully, otherwise you can be confused with error. Okay, because values are very small. All right, so let's for example, okay, so I told you C12 and C13. So let's talk about the C12 C13. Suppose this is a rearrangement reactions. You can see the alpha beta unsaturated ketone. If you are hitting this alpha, okay, this is the what is this dicarboxylic acid. This is the malonic acid. Okay, you can see the 2-carboxylic acid. If you hit, then the rearrangement will take place. The arrows are shown here to give carbon dioxide and this complex is CH2CO OH. Okay, and then it can rearrange it again, so that doesn't matter actually. Okay, so you will get the formaldehyde, formic acid. But that doesn't matter actually. That is the next step. So if you just you can see there is an arrow here. Okay, so here is a carbon center. Okay, if this carbon center it is C12, if you do an experiment it's C12 or C13, then the primary, okay, whatever you will see, that will be the primary kinetic isotope effect. Okay, why? Because you can see that this bond is being broken, isn't it? This carbon, you can see this arrow, right? So this carbon bond, this carbon bond is being broken, right? Is it clear?
Yes, sir.
If it's not, I will write it again. So if we do the isotopic leveling of this carbon and this carbonyl carbon, and you can see this carbon bond is being broken. Okay, you can see the arrow. So you will see the primary kinetic isotope effect. Carbon primary kinetic isotope effect, because CC bond is broken in the transition state or rate determining step. And if you see this, again I go, what is the value of CC primary kinetic isotope effect? You can see for this carbon, okay, this is 1.065 and this carbonyl carbon 1.076. You can see 1 means no primary kind, no isotope effect, okay, and it is how much it is? Less than 1.1. So it is very small amount. Okay, this value is very small. Easily you can get an error. Okay, so not only for if it is difficult to do that, not only for that C13 is much less abundant. So if you want to make a substrate with C13 labeling, it will add up your cost of your experiment, because the substrate will be quite expensive compared to deuterated one. Okay, as I told, deuterated substrates are much easy to afford. It is relatively cheaper, not very, but it's still relatively cheaper than substituting a C12 with C13 because of its low abundance. Okay, and not only for that, whatever the primary kinetic isotope, you will see there is small amount. Okay, so you need to do the experiment very carefully. Okay, that is the reason why we focus always for the isotope effect H versus D, not C12 versus C13. But you can do that. This is the experimental value. Okay. The second example you can see here. Okay, this is a kind of SN2 type of reaction. Cyanide is attacking with Cl and then CCl bond is leaving. Okay, to give the benzyl cyanide or Cl minus. So you can see that Cl minus CCl minus is cleaving. So if you do an isotopic replacement with CCl with Cl35 is the most abundant with Cl37. Okay, so definitely you will get the primary kinetic isotope effect, right? Primary kinetic isotope effect, because CCl bond is being broken. So primary kinetic isotope effect for Cl35 versus 37, you can see the value 1.0057. Okay, so that is the reason people don't do much about the isotope experiments with other atom other than hydrogen and deuterium. Is it clear?
Yes,
I
sir.
think this is the end. Yeah. So this is the end. Okay. So far, the first is to understand what is the nature of the transition state, and not only for that, what is the rate determining step. First is the order of the reaction. Then we discussed about the activation parameters, delays of activation. In last 1 week, we discussed about the various kind of Isotope effect. I hope you enjoyed all these three parameters, okay, to determine the mechanism of reactions, order of the reactions that you are very familiar in Professor Sandeep's and in my lectures, new stuffs, activation parameters, and isotope effects. All right. Any questions? So this is the syllabus for your exam quiz on Saturday. All right. So should I teach hammer flow today or Monday? What do you say? Hello.
So you can start today.
Okay, I'm testing, but what do you would say? Wow, today is 44 people. What happened? If I discuss something about the quiz questions, I never say above 30. But today is a magic day. But still, another 100 people are not here. Right? Okay, definitely. I'll go for further because I'm teaching very slowly. So today is the last, right? Last lecture in October. How many lectures is remaining? And days are going very fast. I thought I just started class probably like 1 week before. I don't know when I started. So when is the last class? I
Sir,
got an email that
2 weeks
Huh?
left.
2 weeks only. Oh my god. 2 weeks, okay. So 2 weeks, but anyway, today is the last class. So Monday, probably 3 lecture. 3, 6. Okay, 6 lecture. Okay. All right. But there is a Diwali. When is the Diwali? 4th is Diwali. Next week is Diwali, right?
Next Thursday.
Next Thursday. So what about our class? I think we have a Saturday class probably. Yeah, probably we'll have a Saturday class. Okay, and we'll have, I think you're second year, right? So I think many of you will have CMP, right? This winter? Do we have? Because we are scheduling to CMP the practical. If you miss in last semester, I think yeah, you people are second year, so you.
So we have registered for CMP labs, but we have not got the exact timetable right now.
Exact timetable, I think we are going to start from December 29th. So we have 1 month left. So yeah, you will be notified. But we will be starting from it is 5 weeks, 29th to I think 27th is the last, or 25th is the last. So it will go on 6 days in a week, and 2 slots, morning and afternoon. Yeah. All right.
Sir,
Any
can you
questions?
tell the batches?
Batch. No, batch has not decided. I think depending on the registrations. Okay. Then it will be, I think, randomly. It is not like that 1 to 20 or 20 to 40. Okay. Because many people may not come now. So depending on the registrations, I think. Okay. I mean, yeah. So we have not allotted any batch like it is 1, 2 in the morning and then again 3, 4. Not like that regular semesters. Okay. So, but I think maximum we can accommodate 680 per class, 87. So around we are planning to accommodate 600 or 650 students to finish the practical in this semester, and the remaining one will be on summer probably. Okay, but depending on your registration, I think you should get an email or something whether you are interested to be practical in this semester, this winter break or not, right?
Sir, approximately how many people would be accommodated for the lab? Like,
Hello?
what would be the vacancy? Like, number of people who would like who would be
Well,
allowed to?
let's see how many, but we are planning up to half of them, like 600.
Okay.
Sir, the practical
Yeah.
start December end, right?
December, which one?
Sir, the CMP lab you just said it will start from December end, right? You said 29 December.
No, November, December. Then November, this is not possible on December end.
That's
Then
right.
how do you enjoy your 1st January and 25th December break? Right?
Yes.
You should have the fun first. For the first priority is the fun and enjoy life, right? Am I correct? Yeah. You already entered in IIT, right? No. Then semester will start. Okay, so it will be in the break. So 29th November. If I tell December, that is my mistake. 29th November, Monday, after your exam is done. All right.
Yes.
Anyway, you will be notified. Don't worry. All right, let's start. So I just talked a couple of minutes just as a break. So if you have any questions, I think if people have doesn't have any questions from isotope effects, I hope I taught in a way the simplest way ever possible. Loose tight, funny names. Okay, you will not get those in books. Loose tight, but it will be easy to remember. All right. Okay, so next is the last one is Hammett plot. Okay, so let me tell you the Hammett plot. What is Hammett plot? Okay, this will also cover, I think, probably 3 class. I think next week will be Hammett plot, at least 2. It is quite long, but quite interesting. But it is a special case. So Hammett plot is very common to determine the rate determining step of organic molecules. So this is a special case, okay, of aromatic compound or organic, or not only for aromatic, so organic compound. Okay, all isotope effects, everything. Yeah, this is we gave the examples SN1, SN2, all the organic reactions, but it can be applied with metals also, metal catalysis. Okay, so if it is a metal is there, then suppose it is cobalt hydride versus cobalt deuterated or deuterated substrate. Okay, so that can be easily isotope effects, rate law, activation parameters. That is the general experimental stuffs. Okay, it can be applied for organic reactions. It can be applied for metal catalyzed reactions or gas phase reactions. Anything. But Hammett is a little special case. It is applicable only in organic compounds. Okay. So this is a general method for examining the changes of charge. Okay, this is very important. So far, activation energy. So no, okay, so let's talk about again the order of the reaction. So what we have learned from order of the reactions. Order of the reactions will tell that how many molecules are involved in the rate determining step, right? Order, how many and which starting material is involved in the rate determining step, right? Which one and how many. Okay, what is activation parameter is telling? Activation parameter is telling that how the entropy will change. Also enthalpy, but entropy is more meaningful. How entropy is changing in the rate determining step. What isotope effect is telling? That how rate constant will change if you replace the hydrogen with its isotope like deuterium. All right. So every different experiments is indicating or will give you a different hint to help you to understand the mechanism. Hammett is telling the charge. Okay, this is a new stuff. It is telling that how charge is building up or how changes of charges of a molecule in the rate determining step or during the reactions. Okay, so changes in charge. As I told again, so changes of entropy, okay, activation parameters of the changes of rate constant values on isotope effect. Here, changes of charge. Very interesting. So before we do that, we need to understand little bit of theory that okay how it is coming and how the Hammett plot will come. So the Hammett plot, this is a plot, okay, like an Eyring plot. You get the Del S value, okay. So Hammett plot, definitely the plot. So we need to first know that what is a plot, okay. What does it mean? So Hammett plot, so have a reference, okay, have a reference. The reference is benzoic acid. Okay, so benzoic acid is one of the simplest and commonly available organic acid, carboxylic acid. It is cheap, it is easy to make, and it has a lot of versatility. Not only for that, it has also a lot of applications. Okay, but regardless, this is a benzoic acid. Okay, so this is the reference. You can see X is the substitutions on the para position. Okay, so this is the reference. So Hammett plot is dependent on the benzoic acid, the reference molecule. All right. So benzoic acid in water, it gives benzoate and H plus. Okay. So is acidic in water, right? So you can see, so the Hammett plot is, I'm going to come later. Okay. But basically how the substituents, it doesn't matter in the meta or para position, but para is the more effective because this is under conjugated depending on the what is the nature of the X. So how the X may be methyl, electron donating groups or electron withdrawing groups, doesn't matter. It's a substitutions, okay, and there is no substitute. If X is H, then this is the benzoic acid. So if we have a substitutions on the para positions of a benzoic acid, then how the X is influencing its acidity of the benzoic acid, okay, or how it is influencing the rate constant of these hydrolysis reactions. Okay, so it is obvious from your high school knowledge, you know that if X is electron withdrawing group, suppose this is a nitro or cyano groups, okay, and not only for that, this is also conjugated. Regardless, this is electron withdrawing groups, okay. So it's the rate constant from left to right, it will increase or decrease this value. If X is electron withdrawing groups, so compared to benzoic acid, the rate constant will increase or decrease?
Increase.
It will increase because it will increase the acidity. Yeah. If X is electron withdrawing groups, then it will be more stabilized, right? It will be more stabilized. Okay. All right. It will be more. It will stabilize more, and it will increase the acidity of benzoic acid. Okay. So the equilibrium with water or these forward reactions will be faster, so rate constant will be more, okay, compared to simple benzoic acid. And if it is electron donating groups, then it will decrease the acidity, right? It will decrease the acidity. All right. So this is so far. This is very simple. So the benzoic acid pKa value, I hope you know pKa value, right? Minus log 10
Yes.
Ka, that you know from your high school. Ka pKa value, yeah, you know that. I'm asking you whether you remember or not. I hope you did remember. Yeah, I have so, right? Even from Professor Sasangdeep's class. Okay. So the pKa of benzoic acid, okay, phenol is around 10. If it is benzoic acid, it is 4.2 in water. Okay, pKa value in water. So obviously, if you donating groups, if it is strong donating groups, then pKa value will increase, that you know, because it is less acidic. And if you just changes the X value from less acidic or even more electron donating groups to more electron withdrawing groups, as it is shown here, then its acidity will increase and pKa value will decrease. Ka value will increase, means pKa value will decrease, right? All right. Okay. Any questions? No. Okay. So you can see this slide. So we are talking about a plot that is called Hammett plot. Okay, so plot is Hammett deduce a equation. So he thought that can we construct? I wrote it here. Can we construct a mathematical relationships between the substitutions of X and acidity. Okay, so if we changes the X, okay, it will affect the charges of arene. Definitely, I'm coming up later, okay, about the charge. We are not talking about the charge yet, okay, but obviously it will affect the charges of the aromatic ring, right? Definitely. And how the X will influence on the acidity or Ka value, and can we deduce an equation? Okay, so after a lot of experiments, Hammett deduced one equation. Okay, so that is Hammett hypothesis. Okay, this part one. There are two things. So he told that, okay, he deduced that if it is a log 10 Ka, okay, acid constant or equilibrium constant for hydrolysis of benzoic acid, X is the substitutions divided by log Ka equal to sigma. Okay, so he first put a value that is called a Hammett parameter, that is the sigma X. Okay, this is the first things he proposed, that okay, he put a parameter that is called Hammett parameter. So sigma X. So if X is H, then what will be the value of sigma? If X is H, then what will be the value of sigma?
0.
It will be 0, because then Kh by K H same, so it will be log 1. Log 1 is value is, what is the value of log 1? Base 10.
0.
0.
0.
So for benzoic acid, the sigma value is 0. All right. So okay, I will. Okay. This is very simple actually. Okay, so let me. Yeah. So you can see here. So how is the values? So I told you that if it is H, then H will be 0, obviously. Okay, now if X is electron donating groups, then what will be the value of sigma? So if X is suppose NH2 or methyl group, then whose value is larger, KH or KX? Which will be the larger?
So what is X? NH2.
NH2 electron donating groups, NH2 or methyl group. What will be the larger, KX or KH? KH, right? If it's donating groups, as I told, that your acid constant will be decrease. So it will be log K, suppose 0.8. So it will be plus or minus? It will be negative because it's log. It's a, yeah. So if sigma value, you can see if it is negative, that indicates that whatever the substitute benzoic acid, that is less acidic than benzoic acid. I told you that benzoic acid is a reference, it is 0. Okay, so sigma value of the reference compound, that is the simple benzoic acid, is 0. So if it is negative, means you can see that if it is negative, then you have electron donating substitutions, means the aromatic ring is electron rich, right? Richer than simple benzoic acid. And if it is electron withdrawing groups, then the sigma value will be positive. Okay, and also depending on the electron donating effect or electron withdrawing effect, the value will also change. For example, the NO2 is much more electron withdrawing than Br, so you can see that sigma value for NO2 is much larger, plus 0.78 compared to Br, that is 0.23. Is it clear? Yes or no?
Yes, sir.
Yes, sir.
Yeah, it is simple. Okay, let me drink a little water. All right. Okay, I think I will finish this slide. Okay, then I will stop. The next, I think I will go more details later. So Hammett is telling, so far you can see the sigma value. You can tell that whatever the substitution you have, that is electron donating or electron withdrawing. Not only for that, the aromatic ring is electron rich or electron poor compared to benzoic acid. So next is this part 2. Hammett proposed that for any kind of substrate, not only for suppose aromatic compound or non-aromatic compound. Okay, suppose you have a this is the benzyl. Okay, so you can see here. Where is my pen? Yeah. So it is not a benzoic acid. Okay, this is there is a methyl groups introduced here. So this benzoic acid is not anymore conjugated with phenyl rings. So Hammett tried to generalize all his relationship, the free energy relationship, okay, log K, okay, the K value with all other substrates. Okay, so he told that log K AX, okay, log 10 KX by H, that is the basically the sigma, it is the same thing, okay, equal to rho into sigma X. Okay. So you look at here. So he is introducing a term here. Where is my slide? Yeah, here is the rho. Okay. Alright. So now let's see what is the magic here. Okay. So now what is the magic here? So look, sigma value is only applicable for benzoic acid. Okay, am I correct? Sigma is only applicable for benzoic acid or substituted benzoic acid. Rho is applicable for any kind of molecule. Okay, I don't know why it comes like this. Okay, rho is applicable for any kind of molecules. Okay, I'm coming about the charge. Okay, so let's talk about the Hammett plot first. What does it mean? So if you have a plot of, so you can see here, if the substrate is benzoic acid, if substrate is benzoic acid, okay, we are studying suppose similar kind of the reactions of this. If substrate is benzoic acid, then what will be the value of rho? What will be the value of rho?
1.
Yeah, because if it is a substrate is benzoic acid, then this is also a sigma X, right? This is also sigma X. If it is benzoic acid, am I correct?
Yes.
This is this. If substrate is benzoic acid, then this is the sigma X, right? So rho will be 1. But if substrate is not a benzoic acid, suppose like this, then the rho value will not be 1. It can be less than 1, it can be greater than 1 or something, and that will give a hint that how charge is building up on an aromatic ring on changing the substitutions. I'm coming up later, maybe next class. Okay. So if you have a plot of log 10 versus K by KH versus sigma, sigma is basically the benzoic acid, and this is, you know that, okay, sigma values are already, you have a table of sigma. I think I have a, okay, I will show you. In the book you can see, or in internet, okay, you have all the list of sigma values. Okay, those are already calculated experimentally. Okay, because sigma is always the same. If it is NH2, it will always be minus 6.66. You can check it also, the values of sigma when X is NH2 in laboratory, because then you need to use the benzoic acid and 4-amino benzoic acid. So sigma value of all the X values, suppose X is cyano, bromo, chloro, fluoro, okay, all the list, everything is already calculated because this is the substrate benzoic acid. Okay, so sigma value, whatever the value it is already deduced. Okay, so how charge is building up, I'm coming up later. Okay, so that all depends on what is the values of rho. So rho is a general term that will tell that how rate constant is changes for any kind of equations with respect to benzoic acid on changing the substitutions. Okay, may not be clear, right? So I'm going to tell again and then I will stop today. Monday we will discuss about examples and more details. Okay, so the Hammett plot, this is a more general plot. Okay, so sigma is based on the benzoic acid or substitute benzoic acid. So rho is the general term. So if you plot for a general equation, suppose this is a equations that what I am telling here. Okay, here this is not a benzoic acid. There is a CH2 groups that is circled in between the carboxylic acid and phenyl. Okay, so how the rate constant will changes on changing the with respect to benzoic acid on changing the substitution of X. Okay, so you can see here if sigma value is less than 1, sigma is 1 means that is the benzoic acid, or if you get a sigma equal to 1 for any reactions, that means that whatever the changes of rate constant you will see on changing the X, that is the same with respect to benzoic acid. Okay, if rho is less than 1, that means this is less sensitive to the substitutions than benzoic acid. If rho is greater than 1, depending on the slope, what is the rho value? Okay, if it is greater than 1, then that means if you change X, suppose you are changing NH2 or methyl with bromide or cyano or NO2, then whatever the charges will build up in the aromatic ring, or whatever the changes in the suppose charge, or whatever the changes in the reactions, that will be more sensitive compared to benzoic acid. Okay, that is the reason. Okay, the rho is called sensitivity constant. This is called sensitivity constant. How sensitive it is. So sigma is what is called sigma. You can see here. Hammett parameter, and rho is what is rho? Sensitivity constant. Okay, sensitivity. Okay, so I will discuss more about this, how Hammett will help you to determine what is the mechanism, what is the nature of the transition state in the rate determining step. Okay, how there are multiple rate determining steps can be possible like SN1, SN2. How Hammett plot will help you to distinguish one from each other. What the value of the rho? Okay, what is the value of the rho will help you to understand what is going on in the rate determining step. Okay, and all are related to the charges. I'm come next. So far I have not told you much about the charges, that I'm going to tell next. Okay, so the rho value is the more important. Okay, so rho value is a positive, negative. What is the value? What is the range of value? If it is 5, what does it mean? If it is -5, what does it mean? If it is +2, what does it mean? If it is -2, what does it mean? That is a scale also. Okay, so it is obvious that if you want to determine the rate rho value, always you have to find the rate constant. Okay, here is equilibrium, that's the equilibrium constant, otherwise you have to determine the rate constant. So always for any kind of things, this is the part of the kinetics, always the first experiment you have to do is reduce the rate law and rate constant. Doesn't matter, everywhere you need rate constant. You need rate constant to determine the activation parameters from Eyring equations. You need rate constant for isotope effects, and not only for that, you need rate constant to determine the sensitivity constant, that is rho value. All right, I'll stop here. Okay, and I think I will take probably 1.5 class or maybe 2 class more. Okay, to finish the Hammett plot. It's very powerful techniques to understand the mechanism. Any questions? If it is not, hello.
Sir, over here, what is the use of saying that rho is 1 when it's benzoic acid? Because sigma would make it anyway 0, right? Because it would be like the log term would become 1, log of 1 would be 0. So like if it is benzoic acid, then why should rho even matter?
Rho, which one?
So in this where your pointer is over here,
Yeah,
if suppose acid is benzoic acid itself, then
that's what I'm telling. Acid is benzoic acid, that is fine. But if any other reactions, any other kind of, suppose this is the reactions. It's an example. Okay. Example. So if this value is also close to 1, okay. You understand? Hello.
yes sir, yes sir.
If value is close to 1, that indicates that whatever the charges will build up on the aromatic ring on changing the X, that is similar to benzoic. I will come up later with examples, then you will realize. Okay. So rho is the it generalized everything. Okay. So sigma is only for benzoic acid. But you will study a mechanism for any kind of reactions. Hydrolysis of ethyl acetate. Acid catalyzed hydrolysis of ethyl acetate, base catalyzed hydrolysis of ethyl acetate. Okay, its rate determining step might be changes. It's different, not the same. Okay, so in the rate determining transition state, the charges, whatever the charge will build up in the aromatic ring or other ring. Okay, so that might be different. And rho value can tell you that which pathway is correct. Okay, so rho is a sensitivity constant for any reaction. Anything. Okay. But base is the benzoic acid, as I told. Okay. That's why X plot is always the value of sigma. Okay. So you have to compare how the charges is building up for any reactions with respect to benzoic acid. Okay, with respect to benzoic acid, the basis, okay, basis is the benzoic acid. So you know that in benzoic acid, if it is electron withdrawing groups, then aromatic groups will be more negatively charged. Okay, right? Because it is pulling the electrons. Okay, so and if it is donating the electrons, okay, it will have different effect. So you know that. Okay, so how it is compared, any for reactions, how the charge will build up, okay, on changing on the X with respect to benzoic acid. So if it is a similar trend, then rho will be positive, and I will come up later. Okay, if it is negative, then definitely it is the reverse effect. Okay, it is a reverse effect. So whatever the effect you will see on electron withdrawing groups on benzoic acid, if rho is negative, means on that particular cases you will see the reverse effect on using a when X is the electron withdrawing groups. Okay. Okay, this is the beginning. So we will come up with more examples with scales. A lot of stuffs are there. It will take 2 more classes. Okay, then you will understand more.
Okay sir.
Yeah. Anything else? If it's not, then I will see you on Saturday. Right?
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
All right. Bye bye.
Thank you sir.
Thank you, sir.
Thank you.